Hello everyone. So in this lecture, we are going to go through the time-independent form of the Schrodinger's equation. And before starting out, I want to just clarify the Schrodinger's equation, the entire form, the most general expression of the Schrodinger's equation is written right here. So this is it. And the reason I'm not going through any derivation of this equation is because there isn't any. This Schrodinger's equation is simply a postulate. It is a postulate made by very smart physicists of the early 20th century, the most prominent of which is Edwin Schrodinger. And it is, it is an equation that simply works and it models reality very, very well. And it has been tested a countless number of times ever since, and it's just a bit shortly, it is a postulate that works very well, and that's why we use it. Now, you can take the most general form of the Schrodinger's equation. You could take this postulate for granted, and from it arrive at the time-independent form of the Schrodinger's equation, which is also useful for many applications. So, if we do that, we will kind of see where it arises at the very least, starting with this postulate. So I ask you guys to simply take this for granted, and throughout the lectures I'm going to explain to you what all the components really mean. And so we can start with that briefly, and you can take this apart and say, well, if you look at the Schrodinger's equation, we have a time-independent part or time-dependent part here, where the left-hand side is only dependent on position, and the right is only dependent on time. And we have a first derivative that changes with time here. The first derivative of the wave function psi changes with time, and we multiply by h bar, which is Planck's constant and an imaginary number. And psi, of course, is a function of position and time. And so this here is sort of like the notorious wave function of our particle. So if we were to model an electron, for example, we can describe its behavior in all of space and all of time if we just simply solve this equation here. So that's a really big deal, being able to describe the particle's position and across all of time. And if you actually plot a wave function, it is indeed a wave. So it'll look something like this, maybe, where we have psi of xt over, let's say, time. And of course you would have another to position. And of course you would have another axis like time, and it would be changing. This wave function would be changing as it goes through time. So anyways, we can take this equation for granted. And sorry, I'm trying to erase this. And then see what the time-independent form looks like. This over here is the potential landscape. And so the electron actually, if it's not, presuming it's not in free space, it's going to see a whole landscape of different potentials. And that's what this models. It's probably one of the most important components of the wave function, which is this potential landscape with respect to position. And this, put briefly, this part of the equation is the kinetic energy component. So it's like the kinetic energy component, you can call it. You can call this the potential energy component of the equation. So, anywho, to get to the time-independent form of the Schrodinger's equation, starting off with our postulate, which is a general form of the Schrodinger's equation, which we know works, we can start with this by separating the variables. So we can take this psi of x, which is our x comma t, which is our general wave function, and separate them into psi, or lowercase psi, of x times phi of t. So we have our position-dependent component and our time-independent or time-dependent component, and we can substitute this in, right? And so before doing that, let's just take the double derivative like we see here and the single derivative with respect to time like we see here. So we have, what do we have? Minus del squared psi of dx squared is equal to, what would this be? Phi of t times d squared lowercase phi of x over dx squared. So here we can see that now, instead of having a partial derivative like I have over here, I just have a normal derivative here, because now I am differentiating a function that is only a function of one variable. So I no longer need a partial symbol, right? And I can do the same thing with the position or the time dependent component. So you can see my capital psi looks a little different than my lowercase psi. So this would look like my phi of x, or psi of x, times d phi of t over dt, right? And so I can substitute these guys into the Schrodinger's equation above. And I have this equation down below. So I have my psi times d phi of dt, and this d squared psi over dx squared times phi. And of course, my potential here is multiplied by both psi and phi, right? Both of these are multiplied by my potential. As you can see over here, it's just a direct multiplication of both functions. So, and I can, given the separation of variable techniques, one of the things that we really want to do is we want to separate these variables to both sides of the equation. And we can do that by multiplying both sides here by 1 over phi, or psi phi. And we can do that to both sides, right? 1 over psi phi, right? And these cancel out. And what you're left with is we actually have 1 over psi of x times d squared psi of x over dx squared. And on the left-hand side, we have 1 over phi of t times d phi over dt. So what do we have here? I mean, now, unlike before, we have two different variables on both sides of the equation, or we have one variable on each side of the equation. We have the time, or the position dependent, and we have the time dependent form, right? And if you recall the separation of variables technique, what it says is that when you have both sides of the equation dependent on different variables, right, then the only way that this can be true is if both sides of the equation, the left and the right-hand side, are equal to a constant. So they must equal some constant. They can't, these sides can't equal something that changes along position, because I mean, if something changes along position, it's not going to change on time, and if something changes in time, it's not going to change in position. And so both sides of the equation have to be equal to some constant, and we can set that constant equal to whatever we want. It's quite arbitrary. We note that if you were actually to work out the units of all of this, and we indeed see it here over here with the v of x, the units of both sides of the equation are energy. It's joules, simply joules, or electron volts. And so we can set that equal to energy, and that is precisely what we do. We choose a variable for energy, a constant for energy, and that is E. We're just going to choose E here. And we set the left-hand side, this time-dependent side, equal to our constant, right, which is E. And we can divide everything over and rearrange it to look like this, right? So probably most appropriately, I should circle in this guy here. And the right-hand side, this position-dependent side, can be equal to this variable here. And this, folks, is, here is the time-independent form of the Schrodinger equation. So time-independent Schrodinger equation. So we started off with our postulate of the normal Schrodinger equation, and we sort of worked our way into the time-independent form of the Schrodinger equation. Most commonly, it is expressed as follows. We can multiply both sides by psi, and we end up with this. This is all multiplied by psi, and this is equal to E times psi. Right, so we can substitute, this back in and, get this form of the equation again. But this is the most common way we write this. And if you notice here, and the biggest takeaway to get from this is that this is an eigenvalue problem. This is an eigenequation. Eigenequation. Why is it an eigenequation? Well, obviously it's because we have an operator, A, multiplied by our function psi, and this is equal to our eigenvalue E multiplied by that same function psi. Or, this simply has our form A y is equal to lambda y. And this is an eigenvalue problem, right? This is our classical, in a bunch of textbooks we have A y is equal to lambda y. This is our so-called eigenvalue, our eigenequation form here. And so we indeed have an eigenvalue problem up above in this time-independent form of the Schrodinger's equation. And just to be a bit more concrete here, our operator, this is generally called our operator, since this is an energy eigenvalue problem, it is most commonly referred to as our Hamiltonian. So whenever you see the word Hamiltonian, you know that we're talking about our operator here, this operator. So our Hamiltonian is just this the summation of the kinetic component and the potential energy. It's sort of like the total energy of the system. Here, this wave here, there's several words for it. We call it an eigenfunction, which is kind of like what a mathematician would call it. In quantum mechanics, you would call it an eigenstate or a wave function. In some places you'd call this an eigenvector, or some disciplines you'd call it an eigenvector. And this is called our eigenvalue. We also tend to call it an eigenenergy in quantum mechanics. Eigenenergy. Oftentimes you see energy eigenvalue. Eigenvalue. There's some ways of writing that. And so this is an eigenvalue problem. That's probably the most important takeaway to get from this. The time-independent form of the Schrodinger equation is simply an operator which operates on a position-dependent, time-independent wave function. This just gives us a scaled version of our same wave function, which is scaled by a factor of our eigenvalue E. And so and there is another way of calculating this one, which I'm not going to go into. You can also come to this equation using the Helmholtz equation. And, let me know in, the comments if you actually want to see how that's derived. You can literally start with the Helmholtz equation, which is, d squared. What is a Helmholtz equation? Yeah, it's d squared psi over dx squared is equal to minus k squared psi, where this was our wave vector, which was simply equal to 2 pi over the wavelength of our wave function, lambda. You can start with this and use de Broglie's hypothesis. Lambda is equal to p over h, h over p. And actually arrive at this same time-independent form of the Schrodinger's equation. So let me know if you want to see this derivation. But if not, I'm just going to stop here, and we're going to move on and use this in the infinite potential well problem, and later down the road we're going to apply this to the finite potential wells. And don't worry, I'm going to describe what all of it means, but my goal is for you all to understand simply just what this equation means, what it stands for, and what and how we can apply it, essentially. So I hope this video was insightful and helpful, and I will see you guys in the next video.